to Biological and Biomedical Engineering program. First of all, a big congratulations to each and every one of you. It's not that easy to get admission into Biological and Biomedical Engineering program. It's a very, very stringent process. You have crossed several barriers to get admitted, to take a seat here in this room. Welcome. So the School of Engineering has its origins almost 100 years ago. In 1990, the school started as a unit, agricultural engineering unit within the Ontario Agricultural College, OAC, here in the University of Guelph. You can see a picture that was actually taken in 1919, just a few years down the road when they introduced a photo camera. You can see it's a very panoramic view of the old buildings here in the campus. You can see different tractors. It was taken at a specific tractor workshop, agricultural mechanization workshop. This is part of the agricultural engineering program. It has its roots, evolved, and we got separated from OAC and formed our own unit, Department of Agricultural Engineering, became Biological Engineering Department in 1970, July 1st, Canada Day, we became the School of Engineering. The Biomedical Engineering program is relatively a new program which was introduced in the year 2010, about 6 years ago as of today. And it is a well-recognized and accredited program, which means that we have been gone through all the stringent regulations and the CEAB, Canadian Engineering Education Board accreditation requirements in terms of meeting the standards and the policies. So as you can see here, that's the logo of the Biological Engineering program. It is DNA, double helical DNA. So what exactly is Biological Engineering program means? If you look at the various universities within the country of Canada, there are only 4 universities, just 4 universities that offers this specific program, Biological Engineering. We are unique. So what does the word bio means? Bio? What exactly the word bio means? Yes? Biology. Biology, okay.
Bio means life.
Life, yes, yeah, exactly. So the word bio means life. When you utter the word bio here in Guelph, in the southwest Ontario, in the province of Ontario, in Canada, it resonates not only within Canada but across the whole globe. Because there is a thrust here, mainly considering the Agricultural College, Veterinary College, and also the College of Biological Sciences, the ability to provide realistic solutions for all life forms, like human, animal, plant, food, irrespective of the type of life forms, the ability to deploy design-based solutions using different engineering approaches is unique. So the word resonates. So in the Biological Engineering program, we combine life sciences with engineering principles. So just a flavor of the Biological Engineering program is biosensors. We talk about and study about different concepts regarding food, food engineering, food processing, food safety, how to manufacture food. Once you manufacture food, how we can go about extending the shelf life of the food. What are the different practices we could deploy in manufacturing the food in terms of bringing down the cost, in terms of meeting the sustainability requirements and the energy-related associated costs. Assistive devices such as prosthetic devices or orthopedic screws in a human body, food systems, manufacturing systems, and biomaterials. So how many of you here are in Biological Engineering program, registered and enrolled? Good. And how many of you are in Biomedical Engineering program? It's quite a chunk. Good, good. Undeclared. How many of you are undeclared? 2, 3. So my goal at the end of today's presentation to convince you to take and enroll into Biological Engineering program, if not at least a Biomedical Engineering program. So please consider by the end of the day to make up your mind in terms of enrolling what you want to exactly do for the next 4.5 to 5 years. So, as I said, there are 4 biological engineering programs across Canada. The uniqueness, the specialty of the University of Guelph is design. So design is a gem in the throne of the University of Guelph Engineering School. So we use design principles at different levels, right from the year 1, Design 1, Design 2, 2100, 3100, 4100, which is 41X. In addition to that, there are a variety of courses, irrespective of the streams you are going to enroll in. For example, a bioprocess engineering, or instrumentation design, or a biomechanical design. So there are specific design-oriented courses in terms of the streams you are going to take. So the flavor is associated in strengthening and bringing down the unique aspects in terms of technical skills and technical knowledge in building up the core towards the design-oriented nature. So the biological engineering program is truly integrated with biosciences. In the first 2 years, we will be talking about the basic engineering concepts through various courses. And in the upper years, 3rd year, 4th year, and probably if you are in the 5th year, you don't have 5th year level course. But if you are in the co-op program, you will learn more hands-on approaches in terms of solving realistic problems using the basic concepts you have learned in the year 1 and year 2. So there is a flexibility. So when we look at the alumni from the biological engineering program, it's 1970, today is 2016. So almost 3.5 decades. Our alumni are well placed and employed at different levels, Vice President in GE, to Canadian Food Inspection Agency, to different levels of private, government and other sectors. So because of the unique nature, they feel, more often they make a statement that they feel like a king of all trades or a queen of all trades. So if there is a problem in real life, if they are working as a biological engineer in an industry, when they have to have a conversation with a civil engineer or a mechanical engineer or an electrical engineer, because specific elements of each and every of these different expertise is built into biological engineering program. So they have a better appreciation of the type of understanding in terms of how to solve problems using a variety of engineering solutions and approaches. So the flexibility to explore different areas of application, food processing, food safety, food engineering, instrumentation, pharmacology, and biomaterials. Very brief overview of the program in terms of the biological engineering. What differentiates between biological versus biomedical? The majority of emphasis of biological engineering is on biochemistry and microbiology, and there are some specific electives associated to it in the first and second year. But as you build on, you have the option to choose a specific stream in terms of food engineering or in terms of biomechanical or bioinstrumentation related focus in developing your skill sets. So the key courses under the umbrella of biological engineering program includes bioinstrumentation design, which is a 4th year course, biological systems 1 and 2. So for example, when I drink water, how does that water in my system converts into perspiration as I sweat here? And then when you urinate, how much of water you intake becomes transformed into urine? And how does that whole process happens? So the fundamental understanding, the cell uptake, the conversion processes and the mechanisms and the fundamental principles will be taught in the Biosystems 1 and Biosystems 2 through mass transfer, through heat transfer, and other related technical skill set and concepts associated to biosystems. Biomechanics, engineering design in terms of general as well as more specifically into bioengineering design. One of the popular option is food engineering, minor in food engineering. So you get to take 5 to 4 courses in the Department of Food Science, and in addition you also take about 3 to 4 courses here within the biological engineering program. So you get a major in biological engineering with a minor in food engineering, which is very popular. Main reason is your job is almost guaranteed. If you want to work in a food industry, food processing industry, or a food safety related industry or a government job, then this is the better option to enroll in. Yesterday, the Minister of Science, Duncan, announced in Waterloo that University of Guelph has been awarded $76 million. $76 million for food-related activities, teaching and research to the University of Guelph. So that is a bigger funding, which means that we get translated into different levels in terms of reviving, in terms of rejuvenating, bringing up the food engineering program within the School of Engineering. So again, you look at a big country, Canada, which is the 3rd largest country by area in the whole globe. When we look at Southwest Ontario, we have about almost 800 food manufacturing and food processing industries within Southwest Ontario. It is a hub. When we take Guelph, the city of Guelph, we have about 55 key scientists, national and globally recognized, highly achieved scientists within the city of Guelph. So not only within the University of Guelph, we have Agriculture Agri-Food Canada, Guelph Food Technology Centre, and the OMAFRA, Ministry of Agriculture, Food and Rural Affairs. So there is a very much high-level expertise available within the city of Guelph, which you will never find in any other parts of Canada. So the city itself is designed in such a way to offer novelty, to to project itself as a hub for food engineering, food-related research. So the 3 undeclared folks, you may want to consider enrolling into food engineering. It's very popular because of the type of courses you will be taking in food science department. You will be actually dealing with a variety of foods, ice creams to cheese to whatnot. There are 3D food printing and so on and so forth. So there is a lot of infrastructure and a lot of new avenues available in the food engineering option. You can see the logo here. This is a biomedical engineering logo. What exactly is this? What is that? Yes?
Electrocardiogram.
Cardiogram, yes, yeah. So it could be a signal output from an ECG or EMG. Cardiogram referred more closely. So the biomedical engineering program combines applied sciences, electronics, mechanical devices, and provide solutions to life sciences. So when we look at the whole bigger umbrella of biomedical engineering, we can divide into 2 units or 2 sections. Stream 1, primarily electrical oriented. So when we list the courses and the electrical oriented, we have medical imaging modalities, signal processing, instrumentation design. These all come under the electrical oriented courses. When we look at the mechanical oriented courses, we have the biomechanical, biomaterials, mechanics 2, and so on and so forth. So we can generally divide, but also there is a little bit of chemical aspects to it. If you happen to take additional electives related to biochem, then you also get to have a flavor of chemistry or biochemical related knowledge and technical skill sets as you build on to become a biomedical engineer. So bioinstrumentation design, biomechanics, and biosignal processing. These are the top 3 courses in terms of the flavor that is being provided in the biomedical engineering program. So once again, it's a combination of engineering sciences, life sciences, and the experience and expertise. So because of the very heavy focus on design aspects, we are going to see a video at the end of today's presentation just to have a glimpse of the type of project students do here as they move on during the 3rd and 4th year of the biomedical engineering program. So they do solve real-life problems using the concepts they learn in the courses. For example, in the third year level, biomechanical engineering design, a couple of years ago, we invited High Commissioner and Ministry of External Affairs from Italian Trade Commission to come and judge the students' projects. The students were actually given prizes. They were really, really good prize. I think it was $3,000 cash for the first prize, followed by $2,000 and $1,000 cash. So they do get recognized because of the ability to solve problems in a realistic manner. So in the first year, engineering science, basic biology courses, for example, you do get to take anatomy and physiology in the biomedical sciences department, which comes under the Ontario Veterinary College umbrella. So you get to have a flavor of how does the human body works. You do indeed really have a chance to see a cadaver, a dead body, during one of the lab component as you take one of these courses. And what is the principles of disease? How does disease occurs? When the body is at ease, it's ease. There is a disease. How does it happen? What is the principle behind it? What is the cellular mechanisms and the changes that occurs in the human body? So the main reason these courses are designed strategically in such a way that as soon as you graduate, you have a better probability, a better chance of getting admitted into a medical school. Those who have aspirations to become a medical doctor, we have quite a few folks, a couple of them, they do get admitted into medical school. It's lots of dedication and sincere efforts are needed over the period of 4.5, 5 years to be able to accomplish an admission into medical school. In addition, you also get to take courses such as basic mathematics, physics and chemistry, mechanics, fluids and thermodynamics. So these courses are common in the first year level as well as second year level for all the 7 programs. So can anyone list me or name me the 7 programs within the School of Engineering? How many? What are they? Can anybody list the names of the 7 programs within the School of Engineering? Biological, biomedical. What else? Yes.
Environmental, yes. Water resources, mechanical, engineer. No, something with computer.
Computer engineering. Okay.
And there's something with the EC.
Yes, that's a weird one. Yes.
Yeah.
Engineering systems and computing. It's kind of similar to electrical. Yes. So that's correct.
Software.
Computer engineering is more of a software engineering, but we do have software engineering that does not fall under the umbrella of School of Engineering.
Okay.
That's another weird program. So again, electives. So you are not. There is no restriction in terms of the electives. Please correct me, Kim. So you have the choice as you build up in terms of meeting the course requirements towards your degree completion. You can take additional electives. If you have a specific interest, go and take philosophy, or go and take history, go and take biochemical. For example, electrical and mechanical are the 2 major flavors within biomedical engineering. But you do feel that you want to build a chemistry flavor to it, then you go and take courses in biochemistry or the Department of Chemistry to build on, as long as you meet the prerequisites for that particular course. So biomechanics, advanced mechanics, biomechanics deals with biomechanics of injury and biomechanical design. In terms of bioinstrumentation, the course talks about designing real-time sensors and transducers, sensor interface design. For example, can you be able to build a sensor to predict breast cancer? When you become 18, the female, so the Canadian healthcare system allows every 2 years to legally check for breast cancer. But the common technology is mammogram, but can we be able to predict it just from the droplet of blood? So how do we go about build a sensor to be able to predict even before it occurs? Those kind of fundamental concepts are inbuilt and integrated into the bioinstrumentation design course. Biosignals, signal processing, medical imaging, biomedical signals, and digital control related courses you will be taking in the upper years. So what are the commonality between the biological and biomedical engineering program? Biological, again, it's much more focused on food engineering, food safety and processing, a little bit on pharmaceuticals, and biomaterials and human systems, while in biomedical engineering, it's more focused on human health and human-based medicine-related technology. They overlap. The first and second year, you tend to take many courses similarly. And then also the third year, thermodynamics and fluid mechanics, these are all the common courses you would be taking, irrespective of the type of program you are enrolled in. So where does our alumni work? They are being placed in a variety of industries. As GE is one, Canadian Food Inspection Agency, different government sector. Some have gone and even to medical schools. Some are in graduate schools. The employment prospect and success rate is much higher compared to the other programs. Maybe it's a little bold statement, but it is true, mainly because the department, the School of Engineering, was started in 1970 as a biological engineering program. So because of the long history, several hundreds of alumni are well placed at different levels. So the prospect of job and the employment is much brighter for biological engineers, and they are employed in a variety of sectors and variety of industries. So some are in regulatory agencies like watchdogs, and some are in federal and provincial government agencies. Some do design, for example, Atenica Health, which is a company based in Waterloo. There are also a company based in Chicago. Some people do move to down south to work in private industries, startup companies, to be able to bring realistic solutions for the society. Some do work in ergonomics and other move on to other professional programs.
Okay, I'll be quick. My name is Ashutosh Singh, and I'm one of the biological engineering faculty here. Mostly you will be interacting with me in your third year, when you will be taking the courses in biosystems engineering, or bioengineering systems 2. And also your heat and mass transfer. That's a core course. That's a core course for all biomedical mechanics, any field you are. Now, as Dr. Trudeau has already explained to you on what exactly biological engineering is, I am much more biased towards it. Biomedical faculty will explain to you. Biological engineering, and the two on particular, please join us. Biological engineering is not just food. Environment, you have medicine, you have any other field I'm missing? Chemical, you have. So the biological engineering is everywhere. It's the mother of all the engineering. That's the way I see it, except the mechanical. Because biologicals don't define. Mechanical, machine. Biological is the mother. Just take that. I said it, you believe it, and we will progress from it. So that's the way we interact with you. That's the way we'll be interacting with you throughout the 4 years here. It's a school, and we are preparing you for the market, right? So heat and mass transfer. Advanced food engineering, that's a graduate course which I teach. Several of our undergraduate students from the previous batch do work in my research group, and some of the undergraduates who have graduated now are my graduate students. I will be interacting with you a lot. If you want to work with me, you can talk to me later on. Research-wise, I work on molecular dynamics and food components. So this is more related to biochemistry, food chemistry, how proteins, you have heard about proteins and carbohydrates. So when you put something in a microwave, or if you're frying something, how does it change the components? How does it change or affect the nutritional content of your product? Those are the things which I use, those are the things which I research on in molecular modeling. I also design new processes or modify old processes to be applied in different other applications of food. And one of my expertise is with respect to high electric field processing. When I say high electric field, I'm talking about 30 to 60,000 volts. You know that. Where to touch it. It just gives you a very bad. And you will remember it for life. But we use that voltage to develop a non-thermal food processing system. So without heat, you can process the food, kill the bacteria, and food is good enough to eat. So those are the type of research which we do. That's molecular modeling of a protein. So I just wanted to show you a diagram of that. So you will see on the very left, on the top, that's the structure, a 3D structure of a protein. Do you know about the 3D structure of a protein? Primary, secondary, tertiary. That's a tertiary structure of a protein. And that is under a microscope. You see how the protein denatures or it opens up, right? But you cannot see that being good or mean grow inside your microscope. Can you see that happen? Can you see the protein opening up? You can't. How do you visualize it? That's where we brought in molecular modeling. Molecular modeling is a tool to do this. And it also gives us a lot of information from the molecular atomic point of view, so we can design the processes in such a way to get what we want. That's why I say biological engineering can do anything, because whatever we do, if your mom asks you to do something, you do it, right? Biological engineering is exactly that. Then, new product development. What you see in the hand is a great bonus. After the white wine, how do you produce the white wine? So you have the grapes, you squeeze, you take out the juice, right? Whatever is left is a waste. That's why I say biological engineering also works with the environment. This waste is converted into new food products. We extract antioxidant products, and that can be used to fortify food later on. So different methodologies we can use to do so. So those are the things which I do, and then I will let Dr. Manushish explain it further.
Okay, good morning everyone. You can see my name, Manju, Mishra, and you can call me Manju. And as you can see, I will be teaching in your 5th semester the course that Professor Mithirajan told you about Biosystem 1, which is like Biological Engineering System 1, and which will be dealing with your application of engineering principles to the biological system, and that can go to various applications in industries like food, in like medicine, in manufacturing. It can go to different applications. And some of the examples, as you know, that you use like food grade alcohol, which is for wine, for beer, and several kind of that. Or you can have the alcohol which is the industry grade. That means you use it for other purposes along with in your vehicle. So if you go to certain like kind of Husky, if you have filled your gasoline tank in Husky, you can see that this is always with 10% gasoline. That's a green symbol is there with 10% of your bioalcohol. And this whether it is bioalcohol for food grade or for the pure petroleum grade, all these are obtained through the process from your sugar fermentation, from the natural sugar, through the process of addition of enzymes as well as addition of your the fermentation goes through in different industries. One of the industries is here, the Sleeman Brewery. How many of you knew Sleeman? Sleeman, okay. So these are like they convert that from barley to beer. So similarly, many of the students from this class are already engaged in different brewery in different parts of Ontario and throughout the Canada and other places. Some of your seniors. So that is what like that is the biological system 1. So I will meet with you registered for the course next year in winter. And beside that, I teach the biomaterial course in the graduate level, where it deals with different biological processes along with manufacturing, starting from packaging to automotive parts as well as electronic goods, depending on the nature of the your application or the funding agency. And coming to my research, I do with bioproducts, which is the kind of general term, or biorefinery. So, how many of you knew what is GHG? GHG, G as in go, H as in horse, and G as in go, is greenhouse gas. Okay, so you are, like, it's general knowledge and you are dealing with greenhouse gas every time. That is why today, on the 7th of September, we are like so hot outside. And this is coming from global warming. So this greenhouse gas emission, meaning emission of carbon dioxide, sulfur dioxide, ozone, all these are coming out of our energy production as well as our production of, where from they are coming. We are producing energy, but every day on the road, you get a lot of greenhouse gas coming out in terms of carbon dioxide, sulfur dioxide from your vehicle, from burning of the gasoline, burning of diesel. So all these things are becoming really concerned throughout the world, and my research is dealing with how we can take little steps to reduce the emission of greenhouse gases, to reduce the impact of global warming, as well as to reduce the uses of petroleum. So with this one is coming under a concept called circular economy, where the circular economy is dealing with, you have to reduce and reuse, remanufacture. So that is the basic. So you cannot make something, make a bag or make a bottle and use it and throw. That is called your linear economy. So we are getting out of linear economy and making the circular economy, which is a closed loop system. So as you both pass out from the school and you get out for the jobs, you will be dealing with the circular economy. That is the closed loop, meaning no waste. From the basic, from the starting from manufacturing design, and with intention, you have to build the system so there will be no waste in the system. So as you can see here, these are the different products I deal with. The bioproducts, as you can see, obtained from any renewable resources, and that can be like the first one is biochemical. It could be lactic acid, it could be succinic acid or similar chemical. That you can also get from the petroleum industry. The second one on the top left hand side, it could be any kind of your energy like fuel. That can be bio, like alcohol or biodiesel or biogas or bioelectricity. Then the third kind is the product, meaning whatever the shirt or the dress or this kind of carpet, all can be made from the non-petroleum resources. In that way, you can sustain the existing petroleum as well as you can have like less greenhouse gas emission and you can have a really better and green product and society. So the last one, last but one of course. So this is my laboratory where we deal with your lightweight production. How many of you knew the CAFE standard? Corporate Average Fuel Economy Standard. That is called CAFE standard, which means it is mandatory by 2025 the car should go for 54 miles per gallon or it go 23 kilometers per liter as per the Canadian standard. And for that you need to make the automobiles lightweight. So for lightweighting can be done by different designs using different new materials. That is what one of the research we do. And the right hand side top one, you can use a compostable food packaging and use it and put it in the compost. So this will kind of decompose to carbon dioxide and water. So here are some of the products from our research, which is obtained from the top one, that is a biodegradable one-time single-use coffee ring that is obtained from the waste feedstock, as well as the beans and the flower pot. The left-hand side is some of your film, that is for mulch filling obtained that are biodegradable, as well as the Coca-Cola bottle packaging tray and oil drip tray, all these different parts for different companies are going on, and many of them are already in the marketplace. So whether you go to MooAnalytica, Hardware, Loblo, you can find all these things in the purchasing. Okay, so you all are welcome to contact and see in case you want to do research in the summer and for come back as a graduate student. You all are welcome. So now we welcome to all of you and thank you so much.
For me is a mix between biological program as well as environmental. So I'll see all of you guys in your third year for heat and mass transfer, and I have a fourth year course for physical and chemical water and wastewater treatment. That's an environmental course, but if you're interested, you can also pick it. In the graduate level, I teach process intensification. So if any of you want to go on to your graduate study, it's a course that you can consider. So in terms of my research is also a mixture between environmental and biological engineering. My research is based on waste valorization, which I turn industrial waste and convert them into useful product. I use it both biological as well as chemical waste to do that. And here are just some examples of the research work that I'm doing. Here on the top, I'm using microalgae to extract astaxanthin, which is a very good antioxidant for food and biological use purpose. And also I'm looking at different bacteria as well as fungi to trying to extract rare earth metals, heavy metals from industrial waste. Here, because we have so many waste, and right now the natural resources is depleting from the world, so what we wanted to do is use the waste material and convert them into products. And these are different kind of ways we can do that. And one interesting one is that we'll be looking at here, we're using plants to extract useful products from the waste. So in that way we can eliminate waste as well as eliminate the use of natural resources. So basically, this is my research, and I just want to say welcome to University of Guelph, welcome to School of Engineering, and have fun.
So how many of you are in regular stream and co-op streams? Regular stream? Co-op stream? Majority of you are in co-op stream. 3 undeclared, of course. Professor Manju Mishra mentioned that she's one of the rich faculty in terms of research funding. In addition to her, there are other faculty members and professors. They have the ability and also the provide opportunity to hire you as a summer student or a co-op student for a 4-month term or an 8-month term. So it's a fully funded program. So it is because the laboratory has state-of-the-art infrastructure and equipment. You will be able to deal with, play with, and develop novel solutions using a variety of technologies and equipments in the labs within the professor's research laboratory. So feel free to explore from day 1 onwards. Because if you are going to be a good researcher, you can be a good employee in any industry. The process of research is very intense. The more you learn different technical skill sets at different levels, you will become a better engineer as you grow. So my name is Suresh Nithirajan again. You can call me Suresh or Professor Suresh. I teach a 4th-year course called Bioinstrumentation Design. It is one of the popular courses within the biological and biomedical engineering program, mainly because the students get to play with lots of gadgets. Arduino. How many of you have used Arduino? Yes. So, yes. Texas Instruments and other related microcontroller boards. So you use sensors and transducers and other related circuits components to build real-time prototype to solve real-life solutions as you make progress. Typically during the 3rd or 4th week of November, every year there will be a big celebration, a ceremony that will happen in the atrium. It is called Bioinstrumentation Trade Show. Several industry personnel will be invited to act as judges to judge the theme design project you will be working over the period of 3.5 months. And then you get judged, and the grades will be provided by the industry judges themselves. In terms of research, I developed a variety of sensors for avian influenza, sensors for breast cancer, prediction and detection, studying biofilms, as well as developing novel tools such as microfluidics, mainly focusing on bringing real-life solutions for food safety and biomedical applications. I'm going to show a quick video, just 2-minute video, that will talk about the type of research we do.
Located at the University of Guelph in the Canadian province of Ontario, about an hour from Toronto, is the BioNanoLab. Researchers at the BioNanoLab help keep our food supply safe by improving the way farm animals are diagnosed and treated for health-threatening symptoms, such as ketosis and avian flu. They develop new tools by combining biology, chemistry, and physics with tiny mechanical structures known as bio-nanotechnology. Unhealthy farms not only threaten the lives of livestock, but also the lives of humans. So, Dr. Suresh Natirajan and his team of researchers study the complex behavior of molecular cell mechanisms in order to develop new tools that benefit the agricultural sector. Their research of nanoscale biological systems has led to the development of analytical and diagnostic handheld tools that can emulate a lab in the field. This means animals with health issues can be diagnosed on the spot without waiting hours or days for a test result. The sooner a diagnosis, the quicker a remedy. No lab time also means savings for the producer. So far, the BioNanoLab has developed a biosensor for detecting the cause of milk reduction in dairy cattle, early identification of avian influenza in poultry from cell structure behavior, chromosome imaging that marks genetic disorders, methods of screening pharmaceuticals for their effects on pathogenic bacteria, a microfluidic tissue model that emulates wounds and allows treatment in cases of drug resistance, and a biosensor that quickly detects allergens like peanuts and gluten. And many of these developments are currently being used in the field today. The BioNanoLab has also been researching ways to prevent harmful bacteria from infecting wounds and prevent rejection of implants by using an electric current. The BioNanoLab, generating new discoveries and innovative products that improve the lives of all living things.
So in addition, we also synthesize novel chemicals such as protein-based peptides from soybean. Some of you may be allergic to soybean, but soybean could actually serve as a component to kill cancer and also act as an antimicrobial agent. So it's called biopharmaceuticals. Non-petroleum-based chemical can be produced from plant-based as well as the skins of microorganisms and frogs and other tiny little animals. We can synthesize specific components, specific chemicals such as peptides to act as anti-tumor agents and antimicrobial agents. So that's the type of research we do in addition to the development of biosensors and bioinstrumentation tools. I would invite Professor Dhoni now.
I'll be very quick. Unfortunately, you're not going to see me next year. Normally, I would be teaching a engineering systems analysis course, but I'm going to be kind of a little busy. I was just elected president of Professional Engineers Ontario, so we actually have a history here at Guelph of people being elected. Walter Delansky, Professor Emeritus, I think was elected 4 times, which I'm not going to go Anyway, that's what I'm going to be busy with next year during my sabbatical. I also teach in some processing and some medical imaging work as well. So I'm one of these strange people. I'm often in various programs that sort of help with the ES&C, help with the biomedical. Again, we don't have departments, so we tend to talk. And again, like Emily was talking about, part environmental, part biological. So that's one nice feature about here as well. No, it's middle, right?
No,
That's right. All right. So some of my research comes out of signal processing. Hearing aids, a medical device. Hearing aids nowadays are mostly little computer chips in your ears. They have a program. You program them. Thankfully, they don't run Microsoft Windows. But what algorithms can be used to make sure that the noise cancellation here is different from the noise cancellation, let's say, in your house? And I will pass it on to the next faculty member. I said I'd be quick.
Yeah, I also will be quick. Good morning. So my name is Karen Gordon. I am a professor. I'm a professor here in biomedical engineering as well. I actually went through the biological engineering degree for my undergrad, so I know the ropes. And then went on to do my PhD in orthopedics, so looking at artificial replacement joints and prosthetics. Okay. I teach biomaterials. You'll see me in third year if you're bio or BME, or if you're mechanical, it's an elective option if you're mechanical as well. It's a good course. Starts in a couple days. Watching tomorrow. My research now has been pretty varied since I've come back to Guelph. So I look at joint biomechanics, osteoarthritis, soft tissue mechanics. I do a lot of tissue testing type work, and moving now into wearable tech. This next slide shows a little bit. Is that the border? Yeah. So up in this corner is sort of some of the stuff that I've done here lately, where this is a big device which takes a cadaveric joint and pushes it through its normal motion under its normal load. So this one way up there is for the knee joint, okay? This is a photograph. You can see there's a cadaveric knee right in there. And we've got some hydraulic actuators and cables there to simulate muscle action. And we try to replicate gait that way. And this is really useful for surgeons. So this work was done with a surgeon at UWO in London, Ontario, who was interested in trying to optimize the surgical procedure to insert these. Do you know what those are? Anyone? A meniscus, good. Anyone ever torn their meniscus? Or ACL, yeah. So lots of injuries where the treatment now is surgery, and you might get a replacement meniscus. Where do we get replacement meniscus from? Anybody? Cadavers, donor cadavers, and we're working on artificial materials and tissue engineered materials to get these with. Problem with putting these in for the surgeon is that you can stick them into the joint and they're sewed down, and there's a multitude of different surgical techniques to sew them down. But the biggest issue is that they tend to bulge out in the patient afterwards. So this device, we made it compatible with MRI, which was difficult. But we could get both MRI images and CT images of the knee joint under load during simulated gait. So we could actually see whether or not technique one would result in a bulging meniscus or not. Okay? We're currently working on developing that, developing a similar simulator for the upper extremity, and working with, yeah, she's next, and she's not here, so I'm going to keep going. Working with Michelle Oliver on carpal tunnel syndrome, and using a simulator like you just saw for the wrist that will allow us to stick a wrist in a CT or an MRI and take images as the wrist is moved through relevant motion so that we can see what's happening in that carpal tunnel at that time. So this is Michelle. She's working on that project with me. She teaches second year mechanics, so you'll see her next year, as well as third year engineering biomechanics. So if that's an elective course, if you want to go sort of a more biomechanics type route in your studies. Her research is on occupational biomechanics. She studies whole body vibration and has a big driving simulator, which is pretty cool, in the building, just on the, I guess that's the east side of the building. We're right by the parking lot there. And she does, most of her work sort of revolves around repetitive strain injuries that can be obtained in a workplace. And so, as I mentioned, we're looking at wrist braces together as well that could be worn in the workplace that are have wearable technology instrumented inside them, so that we can tell if during a shift you're hitting a point where you really need to stop and take a break, and sort of assess how much load and how many cycles you have exerted on your wrist. Okay, so this is her drive lab. This is her driving simulator. She's got a car in there. You go in, you put on the virtual reality goggles, and you feel like you're driving. You get sick from it because all the images are moving by you, but you're not actually moving, so it makes you feel sick. So she has a whole fridge full of ginger ale in there as well. I go in there from time to time, don't tell her, when I'm thirsty. And yeah, this is one of her graduate students who just got hired by, this is actually Dr. Joni's daughter, who just is about to finish her master's. It was hired by, which
General Motors.
General Motors.
For their self-driving research division.
That's right. So you've heard about self-driving cars. She is one of 2 engineers who was just hired to work on that research, which is a pretty wicked job, if you ask me.
I'll take her job.
Yeah, no kidding. And then just to point out one other thing about some of the benefits here at Guelph, or some of the things that I really enjoy about Guelph. This is, I believe she says it's a psychology student. I don't know her personally, but this research is interdisciplinary, and this is one of the buzzwords for Guelph, is that we're not compartmentalized in the engineering department. We like to talk to each other. We like to do research together. And as well, we really try to do that interdisciplinary work, where basically the PIs are the principal investigators on all of this drive research that Michelle is doing. She's the engineer. She's working with someone in psychology, and I think there's someone else in another department. And so these students even get to work together. So you have an engineer working with a psychology major, and so on and so on. Okay? And that's another big feature. All right, John here. Oh, I thought I saw him. Okay, so I'll keep going. Okay, so John, this is John Rensman. He is your Associate Director for Undergrad Studies in the school. Okay, so he is overseeing this whole undergraduate program. I did that for a couple of years, it's a big job. He's also teaching second-year design, so you'll see him next year in the design core. And he teaches a 4th-year course in biomechanical engineering design. Okay, so this is an elective course in that biomechanics stream, if that's your interest in BME. His research is also biomechanics focused, and he's done a lot of work with the Vet College, and he also is interested in bone and joint mechanics. Like me, we have a lot of similar interests. And looking at surgical and assistive device design, again, I know he's worked with a lot of vets on helping them optimize surgical procedures as well. Lately he's deviated a little bit more into sports biomechanics. That's on the next slide? No? Okay. He's done some work looking at different paddle designs to minimize drag for kayaking and canoeing, and also at water skiing and the design of your water skis. So I know he's done stuff like that. And he's also working right now on cardiovascular biomechanics, specifically with horses. And given that we don't have a medical school here, we do have the Vet College, and he has developed contacts there, as have I, and that's one of the key things that might be good if you're BME, to know that this does exist, where they give us a medical problem and then we work on it, okay? And for this particular project, racehorses develop a problem where they get overtrained, overworked, and their arteries actually calcify and can burst open, and they can die and have to be put down. It could be potentially similar to some of the cardiovascular diseases that we would see in humans, and they're working on trying to figure out why that's happening. And he's built this his PhD student has built this massive tent that actually simulates the heart and lung flow, that they take the heart and lungs out of a horse and keep them alive for a few hours. It's crazy. Anyway, okay, am I keeping going again? April, 1 more minute. April Kadimi is on a maternity leave right now. She'll be back. She teaches medical image analysis, biomedical signal processing, and design 3. And her research is focused on looking at automated segmentation of images, medical images. So she does a lot of image analysis stuff for more, better, faster diagnosis of different diseases. I know she's done some breast cancer work and some stroke work as well. So she looks at both breast images and brain images. I think any kind of medical image, and she'll look at it. I think we're out of time. But this is Jackie's.
I'm a technician. I run the Biomedical labs. If you do a lab component in your courses, and I'll be there. Also a resource for the 4th year design courses and things like that to come and ask some questions and help with that part of it. I don't know if I have much more to say.
If you are in BioBME, you're going to see
Yeah.
Jackie. Lots. Okay, I think we're out of time, right? Yeah, they probably went in. Maybe we have no time for questions. Maybe we should, if